Just wanted to say welcome to everyone, wherever you are and whenever you are. This is the first session of the Fault-Tolerant Quantum Technologies workshop. So we're running 6 sessions over the next 2 weeks. And we had initially hoped for this conference to be based in Benasque in Spain, the Pyrenees Mountains. Unfortunately, that couldn't happen because of coronavirus. And in the usual Benasque workshop, you'd have kind of light schedule and quite a lot of discussions and additional talks that kind of just organize outside of the core program. So we have a Slack channel. If anyone has any suggestions or things that they want to try and organize and get other participants interested in, then I suggest you post in the #general thread of the Slack channel. We're also encouraging speakers who have access to Slack to go onto Slack after their talk is finished to answer any leftover questions that weren't resolved in the Q&A session. So each talk has its own thread in the Slack channel. During and at the end of talks, you can try and ask questions. So we've got multiple channels that you can try and ask questions over. Slack is the preferred thing because the questions stay there afterwards, so we can kind of deal with them if there wasn't enough time during the session. But you can also, if you want or don't have access to Slack, use the Zoom Q&A or the Zoom chat windows. So me and Yoshka are going to try and monitor those 3 channels. And if a question pops up there, we'll try and pass it on to the speaker. If a question is complex or long enough to warrant unmuting you, or if you just would like to ask the question instead of typing it in text, then just say you have a question and you'd like to be unmuted and we can arrange to unmute you. But if it's just simpler to ask in text, then do that instead. Okay, if anyone has any questions about the format, just ask them in the chat window now, otherwise we'll start in a second. Okay, we've got quite a few attendees now. Okay, Markus, do you want to put your slides up? Brilliant. So our first speaker of our first session is Markus Müller, who's currently at Aachen in Germany and also Jülich. And he's going to be talking about fighting qubit loss and topological quantum error correction codes. Okay. Thank you, Markus.
Thank you very much. First of all, thanks to Earl, Steve, and Barbara for the kind invitation. It's a great pleasure to open this webinar, and thanks for making this possible despite the pandemic here in this online way. So let me start by pointing out that since October last year, my group is now, as you pointed out, in Aachen and Jülich, and it's really great to be there, part of a bigger team with a lot of quantum information related activities in the area of quantum error correction, but also more widely, where I'm now bringing in a bit of expertise in the direction of quantum information processing with the AMO systems. And all this in a very international environment where I have the pleasure to work at this phase boundary, if you want, between beer, cheese, and French fries. So best of all worlds combined. Okay, good. So what will I be covering in my talk? I would like to start simply to get everybody on the same page with a very basic and short introduction to some notation, stabilizer, quantum error correcting codes, and in particular the surface and color codes that will play a role then later on in the actual topic of my talk, namely on how one can deal with qubit loss in these topological codes, both from a theoretical point of view. And then I'll also be explaining some results from a recent experimental collaboration with the Innsbruck Eintrap group, where some of these concepts have been implemented in the lab. And time permitting, I will then very briefly comment on the wider or some wider activities that go into the direction of realizing experimentally fault-tolerant logical qubits in the regime of beneficial quantum error correction. Okay, so I don't think I have to motivate this a lot here to this audience, but what I hope that comes across throughout my talk is that there are interesting connections between the area of topological quantum error correcting codes and statistical physics models. Most well known is the mapping of these codes to disordered spin models that allow one to determine thresholds in these topological quantum memories. And what I will be talking about is about a noise source, namely qubit loss or leakage, that is perhaps less well studied or less in the focus. And try to highlight some interesting and new connections to percolation physics. Okay, let me get started with a very basic brief motivation of why we need to think about errors. And essentially all quantum technology platforms that we're using today suffer from decoherence and errors. And here, as an example, I've shown from trapped ions, for instance, magnetic field fluctuation that can lead to dephasing and decoherence. And of course, you all know that we can describe these errors by error channels, such as bit flip or phase flip channels, for instance. However, that's not the whole story. As we will see in this talk, there are other error sources such as amplitude damping, leakage, and qubit loss that I'll be focusing on. And I think throughout this workshop, we will also be discussing several aspects, namely that noise details really matter. For instance, coherent versus incoherent noise, biased noise, or correlations that might be present in the noise. So how do we deal with errors? One way of coping with that is obviously with quantum error correcting codes. The simplest example of a stabilizer code would be here this 3-qubit code, where information is stored in 3 qubits. And this is then essentially the simplest system in which one has a 2-dimensional code space, allowing to store one logical superposition here. And then by measuring these stabilizer operators, one can find out about errors that have occurred on the system, and then based on this syndrome information to do a corresponding feedback operation to bring the system back into the code space and hopefully recover the encoded logical operation. So one of the leading candidates to realize this in a scalable way is GitHub's toric or surface code that you see here, where qubits are located on the edges of a 2-dimensional square lattice, and then 4 qubit stabilizers defined on the qubits here of a plaquette are being used to detect bit flip errors, and correspondingly X-type 4 qubit stabilizers can be used to detect phase flip errors on the system. And then logical information is defined within the degenerate code space, if you wish, by string operators that essentially percolate around the lattice here, so on this toric geometry, around the hole or around the handle of this embedding. Another related class of topological codes are color codes. Here they are defined. I focus on 2-dimensional color codes in my talk, on 2-dimensional 3-colorable and trivalent lattices, as you see here, an irregular example where qubits sit at the sides of the lattice, and then stabilizers of both X and Z type are defined on the corresponding plaquettes of the lattice. And here again, this is being used for correction of arbitrary computational errors, and a particular motivation to look into color codes is that they allow for a relatively large set of logical gate operations to be realized in a transversal, that means fault-tolerant and bitwise way. Yeah, so these are the 3 variants. Let's say if you are thinking about renovating your bathroom in 3 colors in a regular lattice, that's the 3 options you have for color code lattices. Let me then just remind you about the logical operators that one can now define here. Let me focus on the toric geometry for simplicity. And what I've marked here in colors are simply the points where essentially the lattice is glued together in the 2 directions. And then what we can see again is that we can introduce string operators of Z and X type, for instance, here along this blue string that traverses the lattice through the blue shrunk lattice. That means here through these blue plaquettes. And similarly, one can have then, for instance, a red logical X or Z operator, the complementary generators, of which one sees that they cross in a single point, and thereby this forms a valid set of logical generators for 2 logical qubits. Similarly, one can introduce red and blue operators in the opposite directions, and then the third color is not a new degree of freedom, but it's linearly dependent on these operators. And what one can verify is that then this allows one to encode 4 logical qubits in this code structure. So one aspect of these logical operators that will become important in the following is that they can be deformed, so that their support is not unique. That's the same as in the toric code here, where you see an example of a deformation of a blue string operator by a multiplication with a stabilizer that acts trivially on the code space, and therefore an equivalent operator simply doing this little detour here would be given by this blue zigzag operator. However, one other type of operators, or another geometric structure, if you wish, of logical operators can be obtained by multiplication here with stabilizers of the same color. And what you see is that under this action, then, for instance, a blue string splits up into a red and a green string, and therefore you can see that an equivalent logical operators can also take this form of string nets, which is unique to color codes, and it's a feature not present in, for instance, the surface code. Okay, so after this very quick overview of some basic topological quantum error correcting codes, let me now move on and speak a bit about how we can deal with qubit loss in these two types of topological codes. So here the question is essentially of how one can deal with a qubit loss that can come in a variety of incarnations. From, for instance, really losing physical particles, like if you think about atomic carriers of qubits, atoms, ions, from a trap, or in other, for instance, solid state architectures, more leakage into outside of the two-dimensional qubit subspace that can be either occurring naturally, for instance, in an atomic system here by decay from a qubit state into some electronic state that is not a qubit state, so that's a leakage process. Or, for instance, if one uses, again, in atomic systems here, hiding pulses, and so that means some pulses where one temporarily parks a qubit in other electronic states so that it does not participate in the dynamics. And then if there are imperfections in this process, that also means that after a number of these pulses, one then leaves some population behind outside of the computational subspace. And the challenge then is to first understand of how we can actually detect these processes, and then also how different quantum error correcting codes can deal with these loss or leakage events. And for the two-dimensional surface code, this was studied in a beautiful a pair of works here by Stacy Barrett and Doherty about 10 years ago, where you see the idea that I just want to briefly summarize here, namely that whenever a physical qubit here of the surface code is being lost, you see that this affects two Z-type stabilizers and two X-type stabilizers on the corresponding vertices. And the recipe to deal with this that was proposed in these works is that one can introduce so-called super plaquettes, where the idea is that one merges two 4-qubit plaquettes, takes the product of the two, and then ends up with a 6-qubit super plaquette where now the lost qubit doesn't participate anymore. So this is a stabilizer that is invariant under the qubit loss here. And one then has actually these two undefined or reduced vertex operators here, also called junk qubits in these works, where one qubit is missing, and that correspond to this reduced vertex operators of weight 3. So what about then logical operators under loss? And here the observation is that if one has a logical string operator, say percolating through the lattice here along the Z-type string, that due to the freedom that we can multiply a logical operator with a plaquette stabilizer, essentially these logical operator can deviate from their path and thereby evade the positions of where a qubit might have been lost, and therefore one ends up with an equivalent operator going this way. So what has then this to do with the question of how many losses can be tolerated, as was shown in these works? This is related to percolation in the following sense, that you see here that with each qubit loss, essentially one link from the square lattice is being deleted. And therefore, after a loss of too many qubits, one sees that a logical operator here, a string percolating through a lattice, doesn't find its way through anymore. And this takes exactly place on a large system at the bond percolation threshold of the two-dimensional square lattice that is at a loss probability of 1/2. So what we studied in a set of works recently is then the equivalent problem on topological color code, where again the question is how to deal with loss, and also then to understand how robust color codes are with regard to loss of qubits, physical qubits from the lattice. And here essentially one needs to find a protocol that allows one to preserve the three colorability and trivalent structure of the code. And what you see here is that a direct generalization of the recipe proposed by Stacy and co-workers is not possible. So we cannot simply take the product of adjacent plaquettes, because then one would not have a valid three colorable lattice structure. And therefore, what we proposed is a recipe that allows one to recover a valid color code with the same number of logically encoded qubit in the following way. So whenever a loss is detected somewhere in the lattice, one does something quite brutal in the sense that one kicks out an additional qubit here, a qubit that we call a twin qubit, that we choose randomly as one of the three neighbors from the lattice. And what one can then now do is one can delete the corresponding 5 links here, this green link in this example, and 2 blue and 2 red links from the lattice, and then introduce now the analogous version of a super plaquette, and that is simply given by this 10 qubit CD plaquette, and then a reduced set of weight 4 stabilizers here on these plaquettes A and B. And what you can verify by doing the counting is that by doing this recipe, we do not introduce new logical qubits, since we simply preserve the Euler characteristics of the surface in which we have embedded the topological code. So now the question is, how robust is this? And what we now will see is that this depends on how we ask the question, namely that logical operators can evade the position of losses by this deformation, or by essentially branching into the other 2 colors if, for instance, one of the lattices, let's say this blue lattice, does no longer allow for percolation of a logical string operator through the lattice. So here's again an example shown pictorially, where we start with the red operator and imagine that we have now losses that prohibit this red operator from percolating here through this red shrunk lattice. What can happen is that this string branches into a green part and a blue part that travel essentially on this shrunk lattices of the complementary 2 colors, and then at some other point here in space, they then reunify and continue essentially as a red operator. And what you see is that then this gives rise to a new type of percolation in these 3 coupled classical lattices that will be essentially the tool to answer whether or we can correct or not for a loss. So let me guide you through this little bit dense slide that shows the results of numerical simulations of this recipe that I just explained of detection and correction of losses. So what you see here along this line is essentially the threshold for different, or the critical loss probability here of around 0.2, 20% for percolation of red string operators through a lattice. So this breaks down here around 20%. And what you see here is essentially different lattice sizes with the thermodynamic limit here on the left. So this is 1 over the code distance to the power of 1 over nu, when nu is the critical exponent that we confirmed to be 4 over 3. That is the critical exponent corresponding to the percolation class in 2D. And what we see is that when a logical red string operator ceases to exist, what we can allow is this branching process, and then what one sees is that this branching process then allows this red operator to continue to exist up to the critical value that corresponds to the point where the blue and the green, so the complementary string operators, stop to percolate on the 2 complementary lattices. Yeah? So around 40% for this example. Now one can ask even more fundamentally what happens if we allow essentially arbitrary branching. So and this corresponds to logical operators that are equivalent to an initial logical operator up to any product of stabilizers of the original code. And this is, one can formulate this obviously as an algebraic problem that can be solved by Gaussian elimination. And what one then finds is a what we call the fundamental threshold under this recipe of qubit loss correction that reaches a robustness of about 46%. That is extremely close to the fundamental limit of 50% that is imposed by the no cloning theorem. So what this shows is that color codes, in this sense, do not differ from surface codes in their high robustness against the qubit losses on the order of 50%. So besides trying to understand this from a numerical point of view, what we then ask ourselves is, can we essentially derive a theoretical understanding of these critical thresholds and perhaps predict them? And here the idea is that one can now derive a systematic series expansion for the fraction of links that are deleted from the corresponding three shrunk lattices of three colors that is given as a series expansion in different powers of P, where P is the loss density or the loss probability per physical qubit in the lattice. And essentially, to give you an idea of the physics that is going on here, you see that if you have a very dense, very low density regime of losses, then essentially losses occur very sparsely in the lattice. Each loss requires one sacrificed qubit to repair the lattice by the recipe that I've been explaining. And this means that these events are essentially independently, or one could say they do not interact. And what you then see is that on average, if you choose the orientation of the sacrificed qubit randomly, you here see, for instance, that here we delete two blue links from the lattice, two red ones and one green one. And if you now average over the three orientations, and you see that on average, one essentially deletes 5/3 links with one loss event from each of the colored, three colored sublattices of the system. So this is essentially this linear behavior in P, 2P times this coefficient. However, now if we go to a higher number of losses, what one sees is then the likelihood that losses occur close to each other in the lattice increases. And you see here the extreme case where, for instance, two losses can just randomly happen at neighboring positions. And then it's quite clear that in this case, we do not need a sacrificed qubit, but one essentially is the sacrificed qubit of the other one. And what you see is that then those are essentially interacting events, and interacting events means that the average or the number of links that are deleted by one loss event from the lattice is now smaller than the number of losses times this R1 coefficient that corresponds to an independent loss event far apart from the others. Here you see another situation where you have two losses together with two sacrificed qubits. And again, the number of links deleted here is smaller than what we would expect. And this is can be captured by essentially an interaction energy, if you want to view it like that, that describes what the difference is of independent losses from this more dense situation. When I kind of calculate these coefficients systematically by looking at locally at the structure, and then in this essentially one has a mean field theory, if you want, that predicts how many links are being deleted as a function of the qubit loss density. So this is how it looks then, and in comparison to the numerical results, you see here the fraction of erased edges from one sublattice here as a function of the qubit loss density. And you see at low qubit loss density, this indeed follows this linear behavior described by this first term. And then at higher loss densities, one has these corrections where one sees that the effect of sacrificing qubits is actually not as bad as one would naively expect, the one for each loss.
We've just got a question asking for a clarification.
Yeah. Sure.
So it's just when a loss occurs, we know it happens and where it is. Is that right? So
that's right. Yes, exactly. We assume that we can detect where a loss occurs. Yes. Okay. So what we then see here is that essentially for all practical purposes, one can describe this with a up to third order very precisely. And if one then looks at the shrunk lattices and essentially goes to Wikipedia, looks up the known bond percolation thresholds, this essentially allows one then to predict at which critical qubit loss density these logical string operators cease to exist. So this is in a nutshell, let's say, the analytical treatment that allows one to understand the robustness of different lattice geometries that can host color codes against qubit loss. Okay, let me then move on and comment a bit on an experimental realization of the protocol that I've been outlining. And obviously, we are not the first ones to think about the effect of leakage and loss. I mean, this has been realized in early works that this is a problematic source of noise, if, in particular, if it's overlooked. One just doesn't take care of reducing or detecting leakage events. And there are different ways to deal with this, either on a code level or with some noise or some leakage reduction units. And in many architectures, there might be actually better ways than the restoration protocol that I will be showing in a second. For instance, if the particle is not being lost really, as has been shown in this recent work by Honeywell, then one can think about smart repumping schemes that simply reinitialize the qubit within the qubit space. So let me then outline, let's say, the minimal system that we've been realizing together with the experimentalists in Innsbruck that correspond to this reconstruction protocol inspired by the work by Stacy and others. So what essentially the essence of this protocol is, as I explained, is that one has this merger of two plaquettes into a super plaquette, and then one has these ill-defined, let's say, reduced plaquettes that one has to measure upon a loss event in order to restore a valid two-dimensional surface code. So the minimal system that allows to explore, let's say, this recipe or this reconstruction strategy is shown here, and that it is composed of 4 physical qubits. So I should say that this is not a complete code, obviously. It's also not the Grussel code, but it's, if you want, the smallest excerpt of a larger 2D surface code as you would have it in a two-dimensional architecture. And the idea is that you start with an encoding. Then what I will guide you through is essentially a strategy in which we can induce loss in a controlled way, detect this loss. This will answer the question in which way we can actually know whether or not a loss has occurred. And then depending on this information, we then do a restoration, or if you want to call it a code switching operation, that allows to map the encoded logical information from this 4-qubit system after a loss onto a 3-qubit stabilizer encoding. So let me guide you through this briefly. So what you see here is a cartoon of the trapped ion quantum computer that has been used by the Innsbruck team, where you have a simplified level scheme and allowing for a qubit manipulation, and then additional states for initialization and readout of the ion trapped qubits. This is an overview of the gate set that is available there. It's a universal gate set composed of single qubit Z rotations, collective Rabi flips of X and Z, X and Y type, and then most importantly, this multi-qubit Mömber-Sunson entangling operation, of which you can think of a pairwise easing interactions of all qubits that participate in this gate. So let me then look at this code or encoding in a little bit more detail. So we start with our 2 Z stabilizers. So we're essentially, due to the smallness of the system, we have this corner here of ZZ here, 1 4-qubit X-type stabilizer, and then, if you wish, very short logical operators for logical Z and logical X that we can and that we need to operate of our 1 encoded qubit in this system here. The encoded basis states are locally equivalent to G at Z states, and this allows actually for a simple preparation procedure that is shown here on the next slide, where one starts in a product state, and in a non-fault tolerant way, one can essentially encode these states by a single application of a 4-qubit Mömber-Sunson entangling operation, followed by a single qubit rotation that determines which state on the logical block sphere we want to encode. What you see here is an example of a Y type eigenstate after the encoding step, where you see that we have a code space population close to 1, And the stabilizers, ideally all +1, are close to 1, not exactly, due to imperfections, obviously, in the involved gate operations. Good. How do we then induce a loss in a controlled way? This is nice in the ion trap. What one can do is one can do this coherently by driving a transition of a controllable length between any of the 2 qubit states to another electronic level, and thereby essentially decide or control any desired loss probability between 0 and 1. After inducing this loss or partial loss, how can we now detect whether or not a loss has occurred on this first qubit? So this has been done by a quantum non-demolition loss detection unit that involves an additional ancilla qubit prepared in a known state called, let's say, 0, and which works in the following way. I'll just give you a flavor of the quantum optics or atomic physics behind it. So the idea is that one essentially wants to probe whether a code qubit has been lost. That means whether it's in one of the states outside of the computational state. And what one can use is that if one tries now to apply a 2 qubit entangling gate, this so-called Mermer-Sørensen gate, the trick or the idea is that this is a 2 photon process that only collectively flips both qubits. However, if one of the qubits has been lost, then the remaining qubit will simply not evolve under this bichromatic light field. And therefore this entangling gate will essentially realize an identity operation or something close to the identity operation on both the ancilla and the code qubit. And then this global rotation will simply rotate the ancilla qubit, and thereby you see that in the case where a loss has occurred, this flips this ancilla qubit to the 1 state, and upon measurement, that then indicates the classical information that a loss has been occurring on this code qubit. On the other hand, if you look at the case where the code qubit has not been lost, so it's an arbitrary quantum state within the computation subspace, then this entangling gate is acting. However, its phase is chosen in such a way that it's not really entangling, but it's doing essentially an entangling operation and a de-entangling operation. So it's simply doing a collective flip. So its effect is like flipping both qubits, and then together with the rotation, essentially it takes this system back to the identity where the code qubit is left unchanged and the lost qubit remains in 0. And therefore, then upon measuring, we would in this case see that no loss has occurred on the system. And this information is then used by the experimentalists to do a restoration protocol. However, before doing this, let me briefly show here how this QND loss detection unit works. So what you see here is the directly measured loss according to the induced loss event and correlated with the detected loss here using this QND unit. And you see that there's a very good correlation, and that what you see on the right is that essentially up to errors on the order of a few percent, this corresponds exactly to the process matrix, or it's more precisely a quantum instrument that corresponds to the case where no loss has been detected, and therefore the information in the code qubit is disturbed as little as is allowed by the quantum mechanical back action on the system.
Markus, we've got another question, which I think is a good point to just read out at this point. So Manuel Morgado has asked, hi, the quantum error correction code is based in which stabilizer operation set? Still Z and X, or MSX and RX? So I guess he's asking for a clarification of what MSX and RX are. Okay, so these are not stabilizers. These are just 2 gates that are available in the trapped ion quantum computer. Yeah, this is simply the decomposition of this QND measurement by which we interrogate whether a code qubit has been lost by these code qubits. It has nothing to do with the initial encoding and the final encoding that we will get to. It's simply a decomposition into the available gate operations. Okay, let me then show what happens in the case of no qubit loss. Yeah, then, well, we should essentially stay in the state where we are, and this, you see, is the case. The only thing is that you see a little bit of dephasing, and this is not an error. That's not experimental imperfections, but this is due to the back action that comes from the fact that if we don't see a loss, we essentially know that with a high probability or higher probability, we have not
been in the zero state from which we induced this artificial leakage. But to a good degree, the code qubit remains in the state where we start. In the other case now, where the measurement of the ancilla indicates that the qubit has been lost, we now have to reinitialize, or we have to initialize in the first place, this 3-qubit stabilizer. That would be here now this stabilizer where the lost qubit has been lost, and after the loss, this is in an undetermined state. And this is can be done by measuring this 3-qubit stabilizer. And please note here that the product of the Z stabilizers is unchanged, and also the logical operators still exist. They can simply be deformed and then have support only on the 3 remaining qubits. Okay, this can be done by a decomposition into available gate sequences. So what this circuit here does, without going into details, it does a projective measurement of this 3-qubit X-type stabilizer, and thereby initializes this stabilizer into a well-defined +1 state. And this is what you see here. Then, if you analyze the state after the restoration operation, this is now a 3-qubit encoding. So we've only 2 non-trivial stabilizers, the product of the Z stabilizers and this newly initialized X-type stabilizer. And what you see is that this initial logical state, the Y eigenstate, is now transformed into a Y eigenstate of this new reduced 3-qubit encoding. Okay, good. I'm probably running briefly in brief out of time. So do I still have 1 minute or 2?
You got a couple of minutes is okay, yeah.
Okay, good. Then I will just very briefly give an idea of let's say some activities in a bit wider context, where we're not only interested in qubit loss error correction, but actually in getting to work a logical qubit based on trapped ions that not only suffers qubit loss or leakage, but also usual computational errors. And this is an effort that we are pursuing here together with this team of groups, both in this Equal project and also the EU quantum technology flagship. And here the idea is, in a nutshell, is to use a segmented ion trap, as they are shown here, that allow one to move ions around to operate on 2 different species. One, for instance, realizing an ancilla qubits, 1 data qubits, together with fast readout and feed forward operations, in order to realize quantum error correction protocols in this setting. And what I give here is a list, and I also would like to advertise Ken Brown's work that is very related to this setting as well, on that is trying to understand under which conditions now the operation of a logical qubit based on experimentally available operations becomes useful. That means that it's better to run in quantum error correcting code than simply encoding and storing information in single physical qubits. And one of the challenges one faces, and I think we hear much more about this in the next talk, is that one has hook errors and that break quantum fault tolerance if one is not careful. So for this smallest 7-qubit color code that we are trying to implement in this consortium, one problem is that when one measures the stabilizers, that single errors can propagate and result in weight 2 errors on the code that would directly result in a logical error. And this obviously breaks fault tolerance. However, very recently, counter strategies that only require minimal numbers of resources have been proposed. And here you see an example of how one can read out a 4-qubit stabilizer here with just 1 additional ancilla qubit, a flag qubit that has been proposed in these works. And that has really now become, let's say, a useful tool in many directions. And yeah, we will hear shortly about this. And the key idea here is that essentially this additional flag qubit raises a warning sign that such a 2-qubit event might have occurred. And then by remeasuring stabilizers, if such an event occurs, and one can essentially track these potentially dangerous situations and thereby restore the fault tolerance, so that this code really allows one to correct an arbitrary single qubit error. And finally, what you see here is, just to give you a rough idea, is numerical simulation results from recent work that we've been doing, in which we model essentially the operation of such a logical qubit in a trapped ion, a segmented trap. And what you see here is that for error parameters that are realistic, that we hope our experimental partners will achieve in the next year or two. The operation of a logical qubit, where the logical error rate is below the error rate of a physical qubit here, starts to become possible. And what you see here is a specific case where we analyzed crosstalk errors that are, for instance, a potentially dangerous error source in this trapped ion setup. And then the dream is that once this is working, one can obviously think then about how one can connect these trapped ion segmented traps into larger arrays. These two-dimensional structures here, I've shown an example of hexagonal structure, but it's not limited to that, in which we could then think of embedding a larger distance logical qubits of different types, couple them to operate with logical CNOT gates, for instance, on them, realize magic state injection, and so on, so that we have really a scalable two-dimensional architecture towards a fault-tolerant, scalable quantum computation. So with this, I would like to end and not run longer. I hope I could convince you that qubit loss is an interesting question, both from a theoretical point of view with this connection to population theory. It's practically relevant, and there are strategies, as the experimentalists have shown, to deal with this in a rather general setting. With this, I'd like to thank my group and mention in particular the people involved in the qubit loss work, Davide, Gemma, and David, and on the theory side, Miguel Angel in Madrid, and then also the experimental team with PhD student Roman Stricker and Rainer Blatt's group in Innsbruck that has allowed to realize this protocol there in a minimal setup. Finally, I'd like to thank the funders for their support, and I thank you for your attention and patience. Thank you.
Okay, well, I'm sure everyone thanks Markus for a great talk, kicking off the meeting. So we've got one question in the queue from Matt Steinberg that the host will unmute in a moment, hopefully, but whilst they're doing that, can I just ask a quick question? So you had this slide where you had 3 different ways of finding the percolation threshold. So one was based on just kind of finding a path for one of the logical operators on just say the red split, the red shrunk lattice. And then there was the branching method. And then the third one was just more like brute force. And the thresholds got better as we went 1, 2, 3. But was there some kind of trade-off in terms of the speed at which you could compute those corrections? So like, is it more difficult to do number 3 compared to number 1 computationally?
Yeah, that's true. So they are all, one should however say they're all efficient. Yeah, so here, let's say for this percolation threshold, it's quite simple. Whenever you have a, let's say the remaining graph, you can easily check whether you in polynomial time, essentially with the square of the lattice size, whether you still find a percolating path or not. And this fundamental threshold that corresponds to the question whether any logical operator still exists. So any operator that is equivalent to the initial one up to any combination of stabilizers. This is a Gaussian elimination problem that can also be solved efficiently, but takes a bit more time than the percolation threshold.
Okay, thanks. Yeah. So I believe we have Matt Steinberg on the line. Matt, would you like to ask your question?
Yeah, can you guys hear me?
Yes, you can.
Okay, great. So thanks, Markus, for the talk. I really enjoyed it. But I just had a general question because I'm not super well acquainted with trapped ion quantum computing. And my question involves what sort of practical considerations you would consider when you take a quantum error correcting code and you map it onto the physical trapped ion quantum computing device. So for example, if you're talking about mapping a quantum error correcting code onto a superconducting processor, you have innate connectivity constraints, noise constraints that are unique to the superconducting chip. But so what happens with trapped ions?
Yeah, so here essentially the answer is that whenever you have a linear string in one trapping region, then you don't have connectivity constraints. So that means you can do a gate between ion 2 and ion number 7, because this is the case because gates are mediated by the common vibrational modes. So as long as they belong to the same crystal, you can do this. However, this is not scalable to beyond, say, 20 qubits or so, perhaps 30. And then the idea is that one has these coupled 1D traps, where one really physically moves. You see, I have a cartoon here, where you physically move an ion from one trapping region into another, and can do a gate there.
And this, hello, are you there?
Yeah.
Oh, and this is via these multi-qubit Müller-Sørensen gates, right?
No, so the multi-qubit Müller-Sørensen gates are again gates that act on any qubit that belong to the same string.
Ah, right. Yeah. Okay.
Yeah. But this is limited to so limited to, let's say, on the order of 20 qubits. Yeah. Mm-hmm. So the Innsbruck team, for instance, showed with one Müller-Sørensen gate, you can map a product state to a 14-qubit GHZ state. They showed this some years ago. So that's the idea. But in the end, what you have to do is, like in a Pac-Man scenario, you have to move ions around. What they can also do is they can swap ion crystals. So they are not fixed in space, but you can really change the trapping potential so that you can turn little crystals around, split a crystal off, split an ion from a crystal off, move it into another trapping area, and thereby you get essentially this 2D connectivity. It's not a 2D all-to-all connectivity, and it's actually an interesting question what then ideal embeddings are. Yeah? So where you have this trade-off between as large one-dimensional crystals where you have full connectivity, and then at the order somehow this connecting links, and that can be achieved via the shuttling approach. And one complementary approach, just very briefly, is that one can also couple them via photons and measurements. And this is, for instance, pursued by Chris Monroe's group or David Lucas's group, where you have traps that are where you do not move ions around, but you couple them via photonic links and thereby establish entanglement between qubits belonging to different crystals in different traps.
So, sorry if I just have one last question.
Sure.
And then we'll have to move on to the next speaker, okay?
Okay, sorry. Or okay.
Go on, ask it.
Okay. Yeah, my quick question is just, so it's not at all determined whether or not a two-dimensional lattice structure is the ideal embedding for a quantum error correcting code in this setting, right? Or
I think for practical reasons, let's say you know, I think you need at least a two-dimensional setting eventually, some kind of two-dimensional architecture. Or some other way of coupling one-dimensional system into 2D. With getting away in a scalable way, I don't think it's practical to have everything in 1D, really.
But 3D is off the table.
3D is nice, and I think there are other architectures where I think 3D is easier. Okay, this goes a bit far, but let's say for cold atoms, you can have 3D optical lattices, for instance, where it's possible to address atoms that sit somewhere in a certain layer. So where you have a focus only for qubits that sit in a certain layer, for instance. And with trapped ions, you can also work with three-dimensional crystals, where you have a lot of ions in 3D. However, they're then getting reliable gates on subset of ions is not an easy task. Yeah,
I see.
I think. But it's not impossible.
Thank you, Markus. I suggest we move on to the next talk now. And thank you.
Okay.
There's a couple more questions in the Q&A window, Markus. If you're able to find that, you can try and answer them by text whilst the next speaker is setting up.